we had a student say she was having trouble seeing it for the previous video, seeing the first reaction. So we're going to use a retrosynthesis question to help her, I hope. So we know that a Wittig reaction can make an alkene. How do we know that? We learned it here. A Wittig reaction is the one that made this alkene. So that's just the previous activity, Wittig, and this was the sulfur ylid that is referred to on the next page as well. And if you're looking at this as your final result, the new stuff happened here, and it came back to, what is it? What does it mean? Comes back to? There's a weird arrow here saying some of it comes from here. It's supposed to be an arrow, and it's got a head here, and it also comes from here. Half of it comes from there. And I'm trying to make that look like an arrow, but I'm not very good at this. That's a splitting arrow. Wow, it looks bad. This is an arrow that's split in two. Can you just imagine it? Because you can't see it. It's terrible. Okay, so this thing came from these two things is all I'm trying to say. Okay, just go with my words here, because my picture is just like a brain hemorrhage. I don't know. So how do you make an alkene? Well, you need a carbonyl. I'll tell you, it's aldehyde or ketone, because everything in chapter 16, whatever I say about ketones, works with aldehydes like 99% of the chapter. Maybe 100, because I think I took out the one that doesn't work in the chapter, but that's okay. So you start with a ketone and an ylid that's got a phosphorus in it. So that's our pieces that we have to deconstruct to first. Got it? Oh, I made a new page. Here's the logic. I made that by reacting either the ylid on the left with the carbonyl on the right. Look. Ylid on the left reacted with carbonyl on the right. Just for visual, I'm going to go with that approach. So it's left was the ylid and right's the carbonyl, left and right. Okay? So for the visual, I'm going to say ylid was here. All the carbons used to be here. Here's your retro arrow. Please draw it that way. Don't invent your own retro arrow. It's a blocked out arrow. It's not a reaction. It's the opposite. It's thinking, what was this before? Okay? This is the final result, is what is the target right here. I've drawn it there. Target. What was the target before it became the target? It was a combination of an ylid with a lone pair and a minus and a PPH3 with a plus and a carbonyl. I think you're seeing it a little better now. I think you're seeing it. Got a small problem. 1, 2, 3, 4, 5, 6, 7. Yeah. It's not a small problem. We'll fix it later. Okay. So, ladies and gentlemen, we now have two problems. Where did this thing come from? And I'm telling you, eventually it's coming from an alcohol, because you're told you're starting from an alcohol. And it will always be those words. And where does this thing come from? It has to be an alcohol. Well, let's look backwards, shall we? This piece can be made from an alcohol. I know I don't have it here, but this piece can be made from a 4-carbon alcohol. You got to review your other reactions, everybody. If I needed to make that from an alcohol, which I am forced to in the next problem on the next page, PCC oxidation of alcohols gives ketones if it's a secondary alcohol, aldehyde if it was a primary. Okay? Chapter 10. Any reaction of alcohols is of critical importance when your teacher says every retro is going to have this word in it. You better know reactions of alcohols inside out, or else you can't do these questions. Okay, so oxidation was one of them. So I'm going to make that alcohol, that aldehyde. Sorry, went the wrong way. This aldehyde here came from an alcohol. The alcohol was treated with PCC. Don't worry, I show the reagents when I do my forward synthesis. This is not the forward synthesis, it's the backwards thinking. This is what the chemists that are worth a lot of money do this all the time. They're the ones that are given target molecules that must be made. They've isolated microgram quantities from nature. And now I need kilogram quantities to start a drug trial. And you've only seen that microorganism once in life. We don't know where any of them are, but you got some potential candidates from it, and you need to make large quantities of them now. You are the money guy they're going to, your lab, and all the workers are all your grad students and postdocs. You're just the guy thinking about the retrosynthesis, okay? You're getting the money. So, and notice that this guy's not done. This is not an alcohol with 5 C's or less. Oh, he's got more to this problem than it looks. We'll deal with that later. We have to make this bigger alcohol from smaller alcohols. And we already know from something we did early today how you can make alcohols that are bigger using synthesis. Way back here. Look at this big alcohol. Look at it. It's got a new carbon-carbon bond. Yeah. That's how you can make alcohols bigger. Aldehyde or ketone with a Grignard or an organolithium. We'll do that later. Where's ylid come from? Well, we know the answer to that. Where's ylid come from? Ylid comes from the precursor to an ylid in an acid-base reaction, which comes from an SN2 reaction that made the precursor. So 2 things. And alkyl bromides come from alcohols. We got to know that. Chapter 10. I'd have to say that's a little more important than the PCC reaction, but they're both very important. Okay? So, previous page. You need phosphorus tribromide with an alkyl halide to make the precursor, and the precursor then becomes the ylid. So what was right before the ylid? The precursor. What was right before the precursor? The alkyl bromide, or chloride, or iodide, you pick. Okay, so remember that. What was it before it was an ylid? What was it before it was the ylid? Did somebody say the P word? I thought I heard it. Precursor had an H instead of that anion. And that's the only difference. H instead of the anion. You don't have to draw the H, 6 figures, but it has a plus still. And then that came from alkyl bromide. And that came from alcohol. Not on the previous page. Just going a step back. We don't have that alkyl bromide, but we have this alcohol. We have all alcohols in our back room. I mean, seriously, this back room right here has every alcohol we start our retros with. Sorry? Oh, a retro is always like the big picture. So this retro, she's asking where would this video belong in the learning scheme of things, right? And I would say retro is always big picture. It's after you've learned the reactions, like how they work forward, now you got to start thinking about them backwards. It's the next level. And you can circle this. I'll just use a highlighter because that there is on my list. That's an alcohol with 3 carbons, right? Original problem was this needs to come from an alcohol with less carbons. And I want to remind you that if we had 5 carbons right here, that's 6. 1, 2, 3, 4, 5, that's 6, right? Not bad. these 5, and it's a Grignard or an organolithium. That's an acceptable short form for either one. Grignard or organolithium, right there. And how many new carbons do you need? This is 5. This is 7. Answer, 2. Do you know a reaction that could add 2 new carbons and have the bond to oxygen on the adjacent instead of the attacked carbon? It goes on the adjacent carbon. Let me remind you, Grignards can react with aldehydes or ketones. Grignards can react without organolithiums are interchangeable. Those 2 words, organolithiums and Grignards, are interchangeable. So they can react with aldehydes or ketones to make a new alcohol that has the new bond on the carbon that is the alcohol carbon. So watch how I said that. The new bond is to the carbon that was the carbonyl carbon. Okay, I said it different, sorry. When you do this one, the new bond is here on a carbon adjacent to the alcohol carbon. You do not attack an aldehyde or a ketone to get that result. What did I attack in that example there? Epoxide. So the minimum epoxide is 2 carbons, correct? And we need 2 carbons. Those 2 will combine. Oh, please don't do that. To give that alcohol. Are you seeing it at all? C minus attacks one of the carbons. You break the bond to the O, you get an O minus on the end. O minus on the end becomes OH. And then you just have to say, I know how to make epoxides from, and you have to say, I know how to make Grignards or organolithiums from, and you better show you know what from. The only way we learn to make epoxides, and this will never change, is from alkenes. Alkene, you did not learn how to make an epoxide from anything else. Oh, wait, sulfur ylids today, earlier. You could have used a sulfur ylid too. That would be showing off, actually. Yeah. And Grignards come from bromo or chloroalkane. Squeeze it in. New page. My retro arrows are decomposing here. See that? There you go. That happens a lot. We've got scrap paper over here. We need. And that comes from an alcohol with 5 carbons. I'm going to highlight it. Yeah. Can't highlight this. How come? Can't highlight it. It's not on my list. It's not an alcohol. Oh, we make alkenes from alcohols all the time. It's a revenge reaction. What? You're dehydrating the alcohol instead of the other way around. Good. Yeah. Okay.
So we don't have to write the reagents?
Now you do have to write the reagents, but that is the next part. So on the test, the real words would be perform a retrosynthetic analysis on this target molecule that ends with alcohols of 5 carbons or less. And that's part A. Part B, show the forward synthesis. That's next. That's when you show the reagents that get you from here to the next one, and then from here to the next one, and then to the next one. Okay. Right now we've just started from the end and said, I know how to decompose it to simpler material. That's what you've done. Now you got to bring the materials together. So that'll be activity 4. And activity 5, I think, will be the next one. It's taking a little while. And we'll make sure everybody's got a lot of paper. So forward synthesis. It used to be I made students redraw the end, like this molecule, on over here in a different box, and show how it became this molecule. I think we're sophisticated enough to know he started part B. He's doing it in purple. You ready? Part B was do the forward synthesis. I'm not going to write it down. I'm doing it in purple, and that way I don't have to redraw this molecule. Tell me how to make the alcohol into the alkyl bromide with the same number of carbons. One reagent, used it already today. I think. Maybe we didn't. HBr is probably going to give rearrangement. Not as reliable as this one. I give you a half point for HBr because you would get some of the product, but not a good yield. I always want PBr3. That is the reliable way to convert an OH into a BR. And how do you make that into an organolithium? In which case that would be C- with a lithium plus. That's the one I'm choosing here. I can put lithium plus up here and cross it off like I knew I was going to do that one already. So what chemicals convert an alkyl bromide into an organolithium? I need a chemical and a solvent. I need a cation made that didn't exist before. It was the same element, but it was not a cation. The thing I crossed off needs to be a metal. And it was lithium. And you can't have an alcohol solvent, but you need a solvent, and it needs, in this case, to be inert to all acid-base chemistry. So butane, hexane, well, butane's not a liquid, so we typically use hexane here because it's cheap and it's almost impossible to take a proton off of it. Okay, now we got to make the other piece that's going to react with that organolithium. I need to make this piece so that this can react. So alcohol needs to be treated with something to make it into an alkene. What chemicals will allow that? It's actually just a catalyst and a condition.
H2SO4 with heat.
Yes. H2SO4 with heat. No heat, no reaction. So can't give you full credit. You're making a less stable pi. That's one reason you need the heat. And then reactions that make epoxides from alkenes. There's a couple per acids that have letters, like just letters. It's short. So you can use one of those now. MMPP is a good one. Don't get the letters wrong. It's already a short form. You're not allowed to make mistakes on short form. So you go to chapter 11 and learn all the ways to make epoxides because they're important. And you realize MMPP is really easy to draw on a page. So I am now at the point where I have the organolithium and the epoxide. I need to carefully tell the instructor how they should be mixed to make this thing here. And I'm going to go back because we did it. When we had the no, we didn't do it here. We did it at the beginning of the day. Organolithium with an aldehyde or a ketone or a Grignard, which is the same as an organolithium with an epoxide. So how were they brought together? I need to have the same information on your answer that is here. What was the first thing you did? I took the epoxide and reacted it with what? A Grignard, or in my case on the next page, organolithium. And then the second step was HCl. If you did all together, these two chemicals, you're fired. You don't have a job. Well, you might not exist either. No, seriously, your existence is in jeopardy when you're taking the strongest base we know how to make and reacting it with one of the top 5 acids we know exist. And you're making propane as a side product. Hello, put it together. You've made propane as a side product in a very exothermic reaction. When you have pKa's that disparate, like -5 going towards 50, you're going to get so much heat that it's got to go somewhere, and propane will ignite. You may not exist. So you got to carefully tell me, you know, it's a 2-step process. In lecture, you only lose a 1/4 point. You don't lose your life. So you're okay. All right. So where are we at? Yeah, you're going to say, I want to do it in as little space as possible, because clearly I know you're out of space. You already said so. And I want to, in life, you know, do things concisely, right? So I need to say this first has to mix with the epoxide. And then after that's finished, you add HCl. So what would be a good symbol way to do that? We're just adding what's already on this page. I think I'm going to connect those two with a parenthesis. I'll do it in red because it's kind of cool. I'm going to mix those two in step 1. So say that. In step 1, I'm going to mix the two. That's the only way you can interpret what I drew just now, isn't it? I connected them and I said mix them. And then after they've reacted, what do you add? HCl. That's it, right? 2 HCl. And I hope you know we spent some time talking about it for a reason. I don't want you to say, why did I lose that 1/4 point? I have everything he has. Oh, you didn't number it and say first you mix? Yeah, got to be clear. And then what was the chemical that took an alcohol, primary, and made it into an aldehyde? We used it previously for a secondary alcohol becoming a ketone. Opposite. She said reduction by mistake. It's an oxidation. Did I have it on that page? No. It was before. Whoa, that's too far back. Yeah. But we had we had a side note with PCC up there or something. I'm going to give up soon. Where's PCC at? Is it here? Page before, you promise?
No.
Okay, we're not going to talk about it. Lost cause. Oh. I was at the next page. That's what we're not making a good video now. That's all I'm saying. Then it's not your fault. Oh, PCT finally. I know we talked about it. Yeah, it works for secondary alcohols to become ketones, and you're reviewing this in chapter 10. A reminder, chapter 10, and then you also review in chapter 10 that PCC will take a primary alcohol and make it into an aldehyde. PCC, also in chapter 10. Chapter 10. And now, guys, you just need to mix those. There's no HCl needed this time. So I like my parentheses for when I need to mix. Say, bring these guys together and just say it's going to my product. Straight up reaction to the product. And you know you're not done, right? You just used the chemical you haven't made yet. So you better make it. Alcohol becoming a bromide. We did that earlier on the same retro. PBr3. Yeah, you're getting multiple points for the same simple reactions over and over. That is paying off when you review. And then how do you make that into the precursor to the ylid? PPH3. I got to move everything over because it does not like me writing over there. PPH3. And then the ylid precursor is going to become the ylid in an acid-base reaction, any base that's the conjugate base of an acid with a higher pKa than 30. Remember, that's our new number, isn't it? 30? That's our new number. So we used NH2 minus previously. We could have used H minus because that goes to 35, right? 30's got to go to a bigger number. That's the whole story. So don't give me a base that doesn't become an acid with a pKa 30 or higher. I like H minus because it's so darn small. Just write H minus or KH. Goes to 35, right? That's the one with the lone pair, but you don't need to show me lone pairs unless it's a mechanism. And yeah, and then we're mixing to get the product. That is the end of that one. We will do activity 5, which is the sulfur one next.